Yes, sir.
Good morning, sir.
Good morning.
Sir.
Hello.
Sir, good morning, sir.
Good morning. Good morning. Tell me.
Yeah.
I'm ready.
Yeah, thank you, sir. We'll be shortly starting the session, sir.
No problem. Anytime. Yeah.
Okay. Sir, good morning, sir.
Good morning.
Sir, can you start the presentation, sir? We'll see whether it is participants or not. Huh?
Yeah.
Just present now.
I'll see. Present.
Sir. Hello.
Can you?
Yes, sir. It's visible.
Is it changing?
Yes.
Yes, sir.
Fine,
Yes, sir. Yes, sir. Thank you, sir.
Okay.
Thank you. Shortly, we'll be introducing you, sir. First.
No problem. No problem.
Okay. Thank you. Sound is in.
You're still seeing my presentation?
Yes, sir. Visible, sir.
Okay. Okay.
All the participants, I'll be introducing Dr. Tata Narsing Rao to you all. Dr. Tata Narsing Rao received his PhD degree in chemistry from Banaras Hindu University in 1994. After working at IIT Madras as a research associate, he moved to the University of Tokyo in 1996 as a JSPS postdoctoral fellow and subsequently became lecturer in the same university in 2001. He joined International Advanced Research Center for Powder Metallurgy and New Materials, ARCI, Hyderabad, in 2003 as a senior scientist, and presently he is Scientist G and Associate Director of ARCI. He was also a guest faculty at IIT Hyderabad and University of Hyderabad in the past. He is a recipient of several awards and honors, including Material Research Society of India 2009, Tokyo University of Science President Award in 2014, Academician of Asia Pacific Academy of Materials 2015, Technology Day National Award 2016, received from President of India. Fellow of Telangana and AP Academy of Sciences in 2017 and Bangalore India Nano Innovation Award 2018. Dr. Rao published more than 140 research papers and filed more than 20 patents. His publications got total citation index more than 16,000 with a H index more than 40. Three of the technologies developed by him, his team, were transferred to industry and are commercialized. His research interests include photoelectrochemistry and photocatalysis, diamond electrochemistry, basic and translational research and nanomaterial synthesis and applications. Currently, his research focus is on indigenizing the technology for large-scale synthesis of electrode materials for lithium-ion batteries, supercapacitors, which is a need of the hour for electric vehicle applications. In the present pandemic situation, he has developed the UVC-based disinfection systems, the UVC trolley for hospitals, UVC cabinets for home and office use, UVC baggage system, scan systems for airports, malls, and hotels in collaboration with companies, and the products are already launched in the market. He is presently working on nano-coated self-disinfecting masks and antiviral paints. We welcome you, sir.
Okay. Thank you, madam. And thank you, all the organizers, for giving me this opportunity. And then I think I have 1.5 hours until what time? 11:30, right? Yeah. Okay. Shall I start, ma'am?
Yeah, please, sir. Please, sir.
Yes, sir.
Okay.
Yes, sir.
So, once again, good morning, all of you. So here, the title of the talk, I'm going to talk on high performance nanomaterials for energy storage applications, because this is the recent hot topic in the nation, because the government is looking for implementation of electric mobility in this country to abate the pollution and then to reduce the import cost of the fuels, and thus increase the economy and save the greenery and the health of the national individuals. So ARCI is my name is Tata Singh, and I am Associate Director of International Advanced Research Center for Powder Metallurgy and New Materials, is known as ARCI. And those who are knowing ARCI, they know that we always work on translational materials research and taking a laboratory proven concept to the higher technology readiness level and prove at the prototype level and then transfer to the industries. So I've been successful in several technologies, in powder metallurgy or surface unit coatings and a lot of other solar thermal applications and the nanomaterials itself. So today talk, I just focus on energy storage materials, which is the hot topic as I mentioned to you. And these are essentially the materials for lithium-ion batteries. And lithium-ion batteries are the storage devices what are used in present-day electric vehicles. And then now, so many kind of electric vehicles I will be showing within India, whether it's a Mahindra or Tata or even foreign companies located in India. They're all producing EVs, and government is pushing with a lot of incentives, both for the consumers, buyers, as well as the industries to implement and then push the electric vehicle technology in this country. So let me start with my slides. As I said, ARCI looks for translational research, whatever technology it is. And now if I talk about lithium-ion battery and supercapacitor storage materials and their scale up. So whenever we talk manufacturing, then you can see the gap in manufacturing innovation that is between the left side one is government and the universities like you and I. As we work on laboratory scale research. If we go down, you can see on technology readiness level, TRL. TRL 1 to 3, there is basic technology research in the bottom. Probably I will use my cursor, laser pointer, I hope. Pointer options. Yeah. So, yeah, you can see this, right? So this basic research technology and research to prove feasibility and technology development. So technology development already you start going into 4. So whatever we do in the academic institutes or research laboratories, they always do experiments and stay in this space. And when you want to cross this space to higher TR levels through technology demonstration, that is 5, and 6 and 7 system subsystem development. That means you're already talking about in case of batteries. You make materials and then you make a small coin cell batteries, then make a cylindrical batteries and show that is on par with the commercial benchmark one, and then make a system like a module out of that one, and then showcase whether you want to use this to drive a motor in a vehicle, whether it's a scooter or even bicycle or 3-wheeler, auto rickshaw or car. So even you show at a bicycle level a proof of concept of EV with a module incorporating your own cells made with your own materials, then the companies start coming. So that means you are already at 7. Then system test, launch and operation. That means you're already going to field test and you give your modules to company or cells. Then they start working on your battery or battery materials and then see whether this really what we're talking is true at the field test level. And they also see whether it is already passing all the international standards. There are standard protocols for validation. Those things they will carry out, and then they'll say, okay, we are ready. But in this process of TRLs, the companies also look for whether you have a patent. It's not, if you publish something, then they are not very much interested because it's already in public domain in the form of publication. Anyone can, once you publish a paper, anyone can start their shop with this technology, taking concept from you because it is in a public domain. But if you protect with a patent, that means you file this without publishing, you write a patent and then submit in an Indian patent office by paying some money, and then patent examiner will see whether this can be patented or not with their experts, and then they will grant the patent, or if they have some questions, they'll come back, and finally your patent will be granted. So if you have the patent, that's why when madam is reading my CV, you can see some more than 20 patents. Out of them, I think 10 to 15 are already granted and some more in the pipeline. So after filing patent within a year, once the patent filing date comes, if you want, you can still publish. But we really don't publish because we want to protect the company's interest, because even afterwards I publish, someone can fine tune the process and then develop the technology. So we protect it until a company takes, and then because we get money out of that. So we get money means not individuals. Our ARCI will get a lot of money in terms of technology know fee and royalty, and which in turn indirectly it is a national pride. And the company which takes the technology, they will sell the product and they give the royalty to us, and then they become rich, they employ people and they pay tax to the government, and government becomes rich. Government becomes rich means country becomes, we're all rich. So that's what is the manufacturing within India. Atmanirbhar Bharat. Now our Prime Minister, Honorable Prime Minister talks about, and that is all this about. So the government also looks from the scientists to take this. Right now we are seeing China does that one, and China does that. That's why China is now a superpower almost. It is going to exceed America. And then once they have the power, and then they can arm twist any neighboring countries, including India right now. So we have great manpower and knowledge power, but we always stop at 3, because from technology 3, that is lower hill to upper hill, private sector, the engineering, the gap which requires engineering, that part is missing in this country. That's why we are lagging behind. So if that is not taken care right from the student level itself, you think of entrepreneurship, you think of taking technology to a higher level, and if that thought process doesn't come, and then we'll be standing here, our goal very slowly, but the neighboring giant institute countries, they will go and then they are on twist, and then they try to occupy inch by inch, and then that's what we're going to see soon. So what I suggest now is, with this background, if you understand this part, everyone, see, we have to talk, you have to understand. Even you can go to Google and then technology readiness level, you can download and you can read so many articles and sites. But what I want to say is that from the student level itself, like in abroad, you start thinking about TRLs, technology readiness level. What shall I do? Not a single person can do, but you have to collaborate with, you should have a team. You should have inter-institutional collaboration. For that, you have to excel. Unless you excel, I don't want to collaborate. When I want to collaborate with someone, I will see what I gain also. It is a mutual. It's not one way. Okay. So that is possible, very much possible. And China could do that, and our other countries are able to do that. We can also do that, but that willing should be there. So next slide. I think this slide is not moving. What I should do is, it's not moving, right? Now it's very slow. So the people from the organizers, someone should switch on their mic to respond, because sometimes now you're able to see this, right? Yeah. So example is here, you can see, if you cannot see anything what I'm talking, because on my screen it is possible, then you should tell me, right? Now you are able to see the bottles. It's in nano silver, right?
Yes.
Yeah. This is what, this is one example I'm giving. Many people know who attended my previous talks. This is nano silver suspension for antibacterial application on textiles. We make at laboratory with some students. We work, and then we demonstrate, and then see nice colors because of the size, and the nanoparticle size changes within less than 100 nanometer, whether it's 10, 20, 30. The color also changes because of surface plasma resonance absorption. So, but this has tremendous antibacterial potential. So when you apply on the fabric, but then what happens is, the company asks, can you make this in large quantities? Then the engineering part comes. You can see the next one, where we have to design a reactor in collaboration with a company, and then we made the reactor, and then we demonstrate that these suspensions, what I showed in the small bottles, can be upscaled up to 15 liters per batch. And the company who received this technology, the CEO is standing in front of the reactor and seeing how it is made. Then in the company in Bangalore, they have a similar reactors, a plant is made, and then now they can make hundreds of liters per day. And then eventually they supply this to the garment manufacturers like Color Plus, Wrangler, Jeans, and all these guys, now they apply this. So from laboratory bottle level to the product level, You can buy these shirts. It all goes through this chain because this gap is crossed by us. So that's what is. So nanoparticles has relevance in textile or a lot of applications, whether in metallurgical, mechanical. Many of the properties change. The color will change, magnetic properties will change, boiling point, melting point will change, optical properties, electronic properties, and metallurgical engineering properties like your tensile strength will increase when the grain size comes down. There is Hall patch relation. So a lot of things change. So every sector or every branch, people, students can put their hands in this and then do the nanotechnology. But earlier it was a hype, but now there are technologies which are saturated, which are now freezed. That these are the technologies what nanoparticles can do that. So now the scale what you can see here is again I go to point options. You can see here this is the nanoscale where 10 to 10 square is 100 is in the scale of this is nanometer scale. So when you go beyond that one, it is all micron. So you can see tennis ball is in millimeter to centimeter scale, and you come down, and then virus and antibodies, what we are talking about, COVID, and COVID is a virus which is around 100 nanometer, 100 nanometer scale, and antibodies what are produced in body to fight COVID, even after vaccination or already had immunity, then this will be in this range. So within this range, whether it is a virus or whether it is a medicine, whether it is an antibody or whether it is a material particle, anything, they start showing interesting properties, and that properties may lead to high power, high energy, and high toxicity like this virus. You can see COVID-19, it looks very beautiful, but so dangerous, and it is 100 nanometer particle size. This is well established. Actually, if you see under microscope, transmission electron microscope, these are actual virus particles. They are shown. And the schematic is given like this because on the top of this virus, you have small clusters of spikes which contain proteins and amino acids. And then these things, when the virus comes in touch with your body cells, like start with throat or nozzle, this one, and it just goes and then sticks to the human cell, which also contains the proteins and nucleic acid. And then if they both match each other and like each other, then which usually happen, and they start entering into our human cells and start multiplying our human cells, start replicating their own cells. So most of our cells will get converted. So that is where the danger comes. But if you have strong immunity and then if you have antibodies enough and then they don't let this happen, so they get slowed down and then finally your immunity dominates and then that will go. So nanotechnology has a huge potential to transform people's life, whether it's bad or better, but we always should feel better because although pandemic has disturbed a lot of lives across the globe, but still there are a lot of good things if you're a positive thinker. Now I feel that I'm so happy in this pandemic because my son got 4 months extra time to prepare for JEE advanced, and then now he got 3000 rank and now joining IIT Hyderabad. And I was always worried that he may go in the few months back, but now the semester will start only next March. So several months we always will stay together to each other and then eat together. So a lot of families, they started eating together and then the affection, love, and then experience. All those are wonderful actually. So you have to, but you have to be careful not to get into the wrong track. So, and other advantages are here. COVID-19 lockdown in Delhi, if you see, before lockdown, the photograph, you can see that it is fully foggy and then polluted, and then you cannot see the image of that gate. But on March 30, this photograph is taken, the right side part. And then this is beautiful. It is so clean in the daytime when it is taken because of lockdown, because all the vehicles, traffic is frozen, and there are no more vehicles, and most of the vehicles are diesel or petrol, and they emit only 30% is converted into energy, and remaining all goes into the carbon dioxide, monoxide, and a lot of dust, carbon particles which comes unburnt, hydrocarbons sitting on the carbon particles, both in micron, nano, all size of particles. They just go, and then they start accumulating moisture and dust and all. They grow in size, and then finally you see all this junk. So we cannot stop the vehicles just like that, but COVID could do that one. And then we can see what kind of impact it will have if you stop using the petrol and diesel vehicles, and if you transform to electric vehicles. If you start using electric vehicles, assume that all Delhi electric vehicles are electric, then even today we can see with all this lockdown is unlocked, we can see same image. If it is so, that is what electric vehicle can do this without lockdown. And this was the pollution, what diesel exhaust emissions and all, everyone knows. And if you see the particle distribution, the blue one is mass distribution, where it is more than 0.1 microns, means 100 nanometer. So most of the particles, what comes out of the diesel is submicron particles, and which can go some distance and settle down. But the small fraction of mass, which is less than 100 nanometer blue color, but we may feel happy that, okay, it is a small amount only. But if you see the number, because the particle sizes are very small, the number density is so high, and these are millions of nanoparticles decorated with all these unburnt hydrocarbons and then toxic gases. They go and then sit in your lungs, which are directly transmitting these toxins into your blood, because inhalation toxicity is the worst toxicity. So to abate this, again, once again, electric vehicle is the one. So now, if you see this one, the battery is efficiency 40%, more than 40%. And then ICE in the bottom one, you can see the emitting car, which is running. It is less than 25%. I was telling 30%. I'm kind to oils still, because we work with HPCL probably. Then hydrogen fuel, electric vehicle, all these ones, they're all more than 40. So efficiency, and then they don't emit any gases. So this is the beauty of this technology. And then I always tell people, maybe that slide is not there here, that is the expenditure what you spend on fuel per year, it is 75,000 to 1 lakh, depending on diesel or petrol. But if you spend on electricity, it is only 5 to 10,000 rupees per year. The same 10,000 distance, 10,000 kilometers, you calculate that you are traveling. So for your car to travel 10,000 kilometers, you spend more than 1 lakh on fuel, but you spend only 10,000 rupees or less for current, what you spend. So there is advantage even in the cost. All the electric vehicles are expensive now because we import lithium-ion batteries from China, and that costs 40% of the car cost, whatever electric car you buy. And then if you want to reduce that, in spite of importing, you still can save your money and the environment. And money within 3 years or 4 years, you get all the money back in terms of cost reduction in the consumption. But what I want to say, level that. Just give me a break. I'm sorry, I have to sign some urgent document because we have to send some samples for COVID testing in CCMB. So I have to sign on the document because they have to go. So I'll show some of the work what we're doing on the COVID anti-disinfection also towards the end of this lecture. So my point is that first even you buy today electric vehicle, you are going to save money because you are using current, which is cheaper. Because electricity we are not importing. We have huge solar power, you have wind energy and hydropower, coal energy, lot, and nuclear. But okay, so sorry again. Then if you see in India, auto industry, there are already so many kinds of cars available. You see Tata starting Hyundai Kona Electric. This is there in India. We see on the roads. Tata Tiago and Mahindra Electric KUV now it is launching, and Maruti Suzuki Wagon-R with EV. So all these are already available in the market, but people hesitate because two things. One is charging stations are not well established. There is another thing what actually companies are trying to do here, and the battery cost. Because we import the batteries, the cost of the car is slightly higher than the equivalent of diesel. That's why people still hesitate, because you have to pay money directly rather than waiting for the money to come back after 3-4 years in the form of my cost reduction in the fuel or electricity. So the need of our, and you can see a lot of two-wheelers, three-wheelers, a lot of auto rickshaws. Electric rickshaws are plentifully. You can see more if you go to north. If I go to Benares, I see many of the autos are electric vehicles, but mostly on lead acid battery. And even the buses, Ashok Leyland is now launching buses with lithium-ion batteries. And of course, BYD, one company in China, they supply a lot of buses. And then if you see in Hyderabad itself, from Mahatma Gandhi bus stop to airport, the buses, what they go, they're all electric buses from BYD, again Chinese company. So China has a lot of influence because they work hard and then they mass produce things. And when you mass produce, the cost will go down because the supply is more and demand you're controlling. So all this happens. So if you want to become rich in country. Now, you can see there are only 5 players, LG Chem, CATL, BYD, Panasonic, Tesla. These are the major players who makes batteries and then who sell. And we usually buy from we means in India, the companies, either CATL or BYD, they buy. And because these are Chinese, and Panasonic, Tesla, and LG Chem, they are all other countries which are more expensive and of course high quality. So this is the reason. Still we spend a lot of money on imports, and if you can indigenize the technology of battery, which ARCI is trying to do, and then of course we are partly successful, and then I show some of our slides. So battery usually contains graphite as anode and cathode, lithium cobalt oxide if it's your cell phone, or if it's electric car, there are other batteries like lithium iron phosphate and lithium nickel manganese oxide. Those who work in this area, they are very familiar with all this nomenclature. So lithium is expensive because lithium is not there everywhere. Even in India, lithium is not there. But China has got plenty, and a lot of South America has got Bolivia, Argentina, and all. They have got Chile. They have got a lot of lithium sources. And then these advanced countries like China and Japan and some of these countries, Korea, they go and lease the land or buy the lands of these mines in these South American countries, because South American countries are not so advanced countries. They are underdeveloped or developing. So these people go and then they mine the material, raw material, and they do metallurgically process it and then make in the form of raw sources, lithium carbonate or lithium hydroxide. And these materials are used as precursor material to make these batteries. If I want to make lithium cobalt oxide, I need to start with lithium carbonate and cobalt carbonate, for example. And then when you mix them together and burn it, it becomes LiCoO2 plus carbonate will become carbon dioxide, and carbon dioxide will go out. So once you make, it is not so easy like making a chutney. It is you just take and then mix it, then heat it. So you have to control the particle size. You have to control its crystallinity, phase purity, and a lot of things to make it qualified for a battery. So anyone who makes this material just in lab, they can do that one, but they have to work harder to make it good candidate by studying its phase purity and then impurities and then the particle size, shape and all, and keep studying with a coin cell in your lab. You don't need to make a big cells in if it's normal. Even our lab in Hyderabad, we make materials, lithium-ion battery materials on large scales. Like I said, in lithium silver. Here we make now at the moment. If you come and visit us, we can see our bay. A lot of machines and powders in big dabbas of few kgs of powder. So we went up to the kg level of scale, that is TRL 5-6 level, technology readiness level 5-6 level. And a lot of companies take our material and then they test it both abroad and India, and whether this material is good enough and qualified on par with a benchmark. And while doing so, they also see whether we are cost effective or not. Otherwise, why should they take this material or take this technology? Unless so, always you have to keep that in mind that you are of low cost when making your technology. Otherwise, if you make lithium gold oxide and then which is wonderful, but no one will buy because gold is there. Even cobalt itself is so expensive. Again, we don't have cobalt. Actual cobalt is more expensive than lithium. And cobalt again is there in African countries, Congo. And then all these advanced countries, they buy again those mines and then they get it. Because these poor countries, they don't have technology to refine and then make a pure forms of precursors. That's why they have to sell it at very low cost. So the technology only can make the countries rich. Even you have huge sources of lithium or cobalt. And like Japan and Korea, they don't have any sources, but they are rich enough because they are more technology dependent. And that's what India should do. So all the young people should think in that direction. Otherwise, we are going to leap slowly. And 40% of battery materials cost, 60% of the cost of the batteries, 60% of the cost of is materials. So if you can focus on the material development, then your battery cost finally will come down because other things are not so expensive. So at least you can reduce the cost to 30 to 40% down. That itself makes a big difference. So in India, battery plants are not there at the moment because that's what all government is looking, because there are companies like Mahindra, Tata, they make electric cars, but they import the batteries. Unless you have the battery plants in India, you cannot. For example, Hyderabad now, Hyderabad Batteries Limited, they usually make nickel cadmium and then lead acid and all these batteries and high power batteries also. But now we are in touch with them. We have some small agreements also, non-disclosure. And Hyderabad Batteries Limited itself is coming with some 40 megawatt hour plant in Bangalore highway for the lithium-ion batteries. They're focusing for probably trucks or buses or whatever it is. But then we have a huge mega plant is coming in Gujarat with Suzuki contributing 50%, Toshiba 40%, and Densho, Toyota Densho 10%. So this together, they're making batteries. Already the plant is getting ready to operation because of the pandemic. It's slightly slowed down. But once they start making within the country, people get employment and the cost of the batteries come down and the cost of the cars will come down. And we need more number of plants, battery plants in this country to feed to the electric vehicles. If you want to imagine that all the vehicles, what you see on roads, Hyderabad or mega cities, if they have to be replaced with electric vehicles, the numbers are so huge, the numbers are so huge. So you need to have more number of plants. And the technology within the country, indigenous technology of making materials and batteries is very much need of the hour to go on par with other countries, because we are not so behind in these technologies. So if you can see, now let us go a little bit into the material side. And I already told you that the lithium part of the material is called cathode. Most of the cathodes, like lithium cobalt oxide in our cell phone, Now people use, you can see on the top, if you see the scale, energy scale on this left, the 0 is the 0 reference with the lithium. So versus lithium, because lithium ion battery, how far I can get the voltage. If I have a material with lithium cobalt phosphide on the topmost, I can get 5 volts battery. But there is a danger, because in electrochemistry, you can see in the right side, you have the cathode, lithium iron phosphate, and if you want to use lithium cobalt phosphate, you can use it. But the problem is, I'll tell you, and you have anode, which is graphite usually, because graphite is layered structure, is intercalation happens, the lithium goes in and goes in while you charge it and comes back when you discharge. So this charge discharge happens through the electrolyte. And electrolyte contains organic liquid, ethylene carbonate and diethylene carbonate, ECDEC, with a lithium perfluoride, LiPF6 salt, lithium plus and PF6 minus. These are the ions when you dissolve this salt into the alkaline. And these ions go, and then the lithium travels from to and fro depending on whether you're charging or discharging. So, but what happens is, if you have higher voltage, if you want, then you can see the red region where the electrolyte itself starts decomposing at the electrode. So you start getting some kind of dirty layers on the electrode. So your electrodes may not work for long cycle life. So people get with, suppose LiFePO4, lithium iron phosphate, what is used mostly in electric vehicles. It is in the white region. It is safe because the electrolyte will decompose above 4 volts, but we are still up to 3.2 or 5 volts. So we are safe here. The white range is safe. And graphite is used in the positive, the anode side. There's the negative electrode. So here, graphite is in the red region. But what happens is, graphite, if you don't have graphite, because you cannot use lithium foil, that is dangerous, because lithium, once you expose to air, it gets burnt like sodium. So graphite, instead of lithium, we use graphite, and graphite as a anode is very close to lithium and it gives very good voltage. But the problem is, it also undergoes the electrolyte decomposition happens at this potential, and it will start acting, getting coated with a SCI, solid electrolyte interface. But luckily, there's a lot of research happened here, and then people have optimized the kind of graphite and kind of electrolyte, and that gives a nice SCI layer which protects this and which allows the lithium to flow, but not the electrolyte to decompose anymore. So that happens. So graphite is used in all our batteries. But if you can also use for fast charging, if you want to charge your car in very fast, in minutes. Otherwise, normal batteries, you take hours. Even your lithium battery car, you have to leave in your charging station or plug into your parking lot for 6 to 7 hours. But if you want a charging station on the road while you are on way to your next city, then you have to charge it in half an hour, 10 minutes or even less. So there, you need to have batteries inside your car. If you want to charge it, if you don't mind charging 7 hours and then go to your office and go within the city, that's okay. But if you want fast charging, then you can use lithium titanate and Li4. You can see this is instead of graphite used, but they're compromising this much voltage. My voltage will be only 2 volts instead of 3.5 volts. But I am still in the safe region and I can do very fast charging. But I need more number of batteries because I only have 2 volts. If your motor, electric motor in your car or scooter is of 48 volts, to support it 48 volts, I need that many number of batteries in series. So if I have 2 volt batteries, I need more batteries. If I have 3.5 volt batteries, less number of batteries. But what you want to have long driving range to go to the next cities, or you want very fast charging. So that depends on what material you choose. Now, a lot of public transport vehicles, they would like to use lithium titanate as well because they want fast charging in the bus station. So all your cars or taxis or buses which are within the city, they want to get it charged very fast. So they don't mind because they don't want long range. So they don't mind using LTO and LFP combination with 2 volts. But they are very happy that my car gets charged and then I have no problem and it goes to number of cycles, charge, discharge cycles. So we want to make in India, public transport system is so used, so that's why even the Toyota, Suzuki, they're all looking for LTO batteries as well as, but to make those batteries, the starting materials of lithium iron phosphate and lithium titanate, these two key materials, knowing that India needs these materials, of course, lithium, nickel, cobalt, manganese oxide, slightly higher voltage. These also some high-end cars are looking like Tesla uses lithium, nickel, manganese, cobalt oxide because it's a higher voltage. But the problem here is that it's a cost because cobalt is involved, and there is a issue of stability. But you can manipulate by putting more money. So Tesla car is so expensive. But in India, our cars, there are only few cars of high-end cars you will see on the roads, but majority of the cars are. So you can choose the chemistry, but in India, LiFePO4 combination, LiFePO4 graphite for the long-range vehicles, or LiFePO4 LTO for the public transport or short-range vehicles. So graphite is not an issue, but lithium phosphate, these two materials, one has to. So I'm clear. I hope now the talk will be on these materials. Of course, NMC, like Tesla's one also we're doing, or Chennai group is doing. By the way, we make these materials in Hyderabad at ARCI, but ARCI also has got a research center at Chennai, where we have a pilot plant to make battery in the form of cylindrical cell, and then demonstrate making small modules, and then demonstrate electric scooters and all. So, but we focus on the materials, and they focus on the making it into cells. So together we come with this technology. So this is one, and then now you can see here LFP LTO. LTO means lithium titanate. I showed already, and LFP means lithium iron phosphate. And you can have this combination of battery to get a very good. What I'm showing here is it has a capacity of 170 milliampere per gram. Both the electrodes, 160 to 150, 170. Then they're very flat. That means until when you go this side, you can take the energy out, use it for your scooter, but until you take 90% of your energy, still your voltage remains constant. So your electric vehicle keep moving. But in some of the batteries, if the voltage falls slightly slope, then after some time after running, maybe if you're targeting 300 kilometers or 250 kilometers, maybe you have to be very careful. Like it comes to the reserve in your case of fuel, but here you have to start charging. So these are the things what we focus. So these two materials we try work on, and then lithium iron phosphate is the excellent and then low cost because there is no cobalt. It's only iron, and lithium anyway you have to put the money on that one. And this is invented by John Goodenough, who got Nobel Prize with another two his contemporaries who worked on also, one on technology, Japanese, and another on fundamentals. But he's the person who made the LiFePO4 for the electric vehicle application, 96. But until 2000, it did not see the light of the day because LiFePO4 is electrically insulating. And electrically insulating and not so good conductor is not good for electrode, because electrode should have conductivity for the electricity to be taken out to drive your motor. So then what happened when the nanotechnology came? So in nanotechnology, what happens is when you have a big particle of lithium and phosphate, because it's insulator, the diffusion length of the lithium when it comes to into the particle, it has to swim all through this diffusion length. But if you have nanoparticle, for the same volume, if you have nanoparticle, the diffusion length is small. So each particle, the lithium goes in and come out very fast. So the charging discharge is very fast, and all your material get lithiated in short time, whereas here it takes long time. So if your battery has to be charged for a given time, then it gets charged only, if you can see here, it is only 50 milliampere hour if the size is of 1 to 2 micron lithium and phosphate particles. If you have nanoparticle, here you have 150 million, 3 times more, because it quickly gets lithiated, or when you discharge, it gets delithiated. So the size effect is more important. But you can ask, how is the current taken out? So when the electron comes to the surface very quickly when the lithium goes, and these particles are coated with carbon, and carbon is electrically conducting, you have the current collector. So you have to coat these materials in the form of a thin film with carbon incorporated into that one. And then whenever there is lithiation and delithiation, the electrons go to the current collector. And that is coming through your cell and through the external circuit, and your electric motor will run. So we make the lithium iron phosphate carbon coated with, you can see big machines here, and then we make kilogram quantities of this, and then we are less than the commercial one at the moment, and still further coming down by optimizing the process to further come down. And that's what I'm telling you. Whenever you think of technology, first you also should think about the cost. Otherwise, after spending 1 or 2 years, you know that your cost is so high, and no one even look at your technology, although it is fantastic, but it has no value. So that's why the engineering gap and the valley of death, that happens because if you don't take care, then you are in the valley fallen. But if you can take care of all these aspects, then you will cross. That's what ARCI does. And then cost reduction. So even the equipment, we have an imported equipment, is a milling unit for mixing all the materials, raw materials. It is 100 lakhs. And now we have indigenous material, we can do 3 lakhs. So not only material production, but also cost comes down of the material because of the equipment cost. You can see with this, we have around 120 to 140. And here also it is the same thing, even with the Indian equipment. So what I want to show is that equipment manufacturing, indigenizing, material manufacturing, indigenizing, everything. So you try to maximize the indigenization or making within India, then the cost keeps come down. That's what I could show you here. So easy, and also once you make your Indian based equipment also, then easy adoption of technology. When the industry also like to take, because industry doesn't want to invest on huge new machines with so costly equipment. So you have to think all that, even whether the technology adoption is easy, then you have to start interacting with the industries while you are at TRL 4-5 level. That's what we do. And the other material, lithium titanate, I told you, lithium titanate, which is an anode for the fast charging. And that is also the same thing, because again, it is not so good conductor. So we have to make it in the nano size. So what I am showing is nano size makes a difference. And the Nobel Prize, what Good Enough got, because of LiFePO4 is really seen in the electric vehicles, because they are converted into nano size and carbon coated. And the size has big thing to do, and nanomaterials has big contribution in your energy storage in electric vehicle technology. So lithium titanate also, to reduce the diffusion path, we make this in nanoparticle size, and this is widely used. I told you already that lithium titanate, it may not have high voltage because of 2 volts only, but it can be used for public transport. You can see TATA in Switzerland, they use lithium titanate based batteries for their electric vehicles in trams and buses. So all the research usually starts at the laboratory level, and lithium titanate was, it has taken the leap only very recently. But what we do with our students, one of my young research students, one girl now she's in US, and she joined for PhD, and I gave her a job topic that you start making lithium titanate. I also don't know that lithium titanate may become so famous now, but we are only interested in the fundamental research, how the size affects the kinetics and the charging rates and the capacity improvement and all. And then she made by electrospraying these materials, and luckily she got a nanoparticle, but within the nanoparticle you have nanograins with a donut shaped, like vada kind of shape. So here what happens is your electrolyte diffusion happens through all sides within that, and your charging and discharging is so fast. Now, if you see the bottom ones, when I say C rate, 0.1 C is very slow. 1 C is very fast. That means its full capacity, if I keep the battery charged with a given current, specific current, that can be charged to its full capacity in 1 hour. That's called 1 C. So if I want 3 C, that means I'm giving much faster than its capacity. So I'm dumping currents very fast. So I'm asking the battery to get charged, but sometimes the battery may get abused and then get spoiled if it cannot take it. So your material should take that much current. That means as I go to higher C rates, 10C, the current dumped is so high, it should be. So if you can see here now, it is an imported material and is a donuts here, what my student has made. At 10C rate, if you can see, it's only 35 milliampere per gram is the specific capacity, whereas the donuts what my student made is 100. So it's almost 3 times higher, even at very high fast charging and discharging rates. So that's what LTO, I'm talking about LTO. So we could show that the size of the nano and the shape makes a difference for the charge discharge properties. And today is not just our paper alone. We published in a good journal, high impact journal, small that time. In 2014 actually it was. And now we make this lithium titanate in dabbas, if not donuts, in nanoparticles in kg level material you can see here. And you can see 600 cycles we do, and the charging and discharging remains same. And here we are comparing with Galan one imported material, the red one, which has lower capacity than ours. We are performing much better. And the cost is 14,000 for an imported, even Chinese, and we are at 8,600 in I think it is 2018, the slide, these numbers, but I have to change. Now it is just less than 2,000 rupees cost because we scaled it up and we started using some local technology, material, equipment and all, and we optimize. So now we are very, very cheap, multiple number of times lesser cost compared to imported, and that makes a sense. So now the Toshiba and several companies, they take our materials and they want to test it and see whether really in actual battery making, these materials are working fine. If that happens, then there are companies ready to take this technology to take it to tons level, because tomorrow if Hyderabad Batteries Limited makes the plant 40 megawatt hour, then they need tons and tons of material, and a company should make, ARCI cannot make. So there are companies who are interested and collaborating, and then actually they're testing these milling and all on their side to make tens of kgs for the validation at the commercial level. And another side, these materials are being given to companies to test it, so that total ecosystem is created right from the material making, technology and commercial upscaling and supplying to the battery industries, and making the institute rich and company rich and the nation altogether. We demonstrate, our Chennai people, they demonstrate Chennai plant. They make these materials, use these materials and make plants, batteries, and run some motors and all, as you can see here. And people look at next generation batteries. The next generation battery is what? Lithium sulfur. Lithium sulfur battery, what we do is, I think I have half an hour time, right? I think I can finish it, no problem. So lithium sulfur battery, sulfur has got very, very high energy density. So if you can see the cathode capacity, milliamp hour per gram on the top blue line, and lithium manganese oxide, lithium cobalt oxide, what you use in your cell phones, and it's only 400, right? And all your lithium iron phosphate and all, they're 170, 160 like this here. Okay. But lithium cobalt oxide, lithium cobalt oxide is also here. See, the arrow is, it is written here, but the arrow shows this part. So all these are less than 200 or 150, 170 like that. Whereas sulfur, you can see lithium sulfide, sulfur is lithiate sulfur, 1600. My God. So it is so many times higher, but its voltage is less. It's only 2 volts versus lithium. But if you take lithium cobalt, there are 4 volts. I am compromising on the voltage by 2, but I am increasing multiple number of times the capacity. So the total energy density is capacity into voltage, and if you multiply, then this gives, sulfur gives very high energy density that can be stored. So if you have lithium, and sulfur is very cheap, because our refineries give byproduct is again sulfur, oil refineries, and you can put more number of batteries, and with high energy density, more number of batteries, because your voltage should be in series, right? If you want to drive 48 volts motor, you should have more number of 2 volts batteries than half the number of 4 volt batteries. But your energy density for the energy density means the driving range. If you want to go to Pune or Tirupati, then you use lithium sulfur batteries, which are smaller in size because of high energy density than conventional lithium batteries. So the whole world is looking for lithium sulfur batteries, and ARCI also has initiated in TRL3 level, but we have shown that. But there is a challenge in lithium sulfur battery. Why? Lithium sulfur batteries are known for decades, but it is not implemented because once there is a lithiation problem, discharge, the sulfur takes lithium, they form polysulfides, Li2S8, Li2S, all these are soluble. So from the sulfur, these get soluble in the electrolyte and go to the other electrode, and while discharge, so you lose a lot of sulfur during the shuttling, and then the battery slowly dies. So your dream of getting high energy density will be left for few cycles, unlike maybe 20, 30, 100 cycles. But whereas in actual batteries require 1,000 to 1,500, even 2,000, if you want to really use for electric cars. So can I do that? Can I increase its cycle life by containing these polysulfides without going into the electrolyte? So if you have a sulfur in a carbon matrix, like here you can see porous carbon, and the yellow particles are sulfur, and you embed sulfur into the porous carbon and use that carbon is conducting, and use that as an electrode, then the polysulfide, what is formed, it gets trapped within the pores and it doesn't escape into the electrolyte. So that is one of the strategies. You can see my team at ARCI. It is my student Harimohan, now is in Germany, and recently we published this paper in Energy Materials. And we make carbon from the jute stick and nanoporous graphene-like carbon, and incorporate sulfur into the carbon, and then use this as electrode. And we also have the separator, which is coated with this kind of carbon, so that any polysulfide, it gets trapped in the electrode, and a little bit coming out will get trapped on the carbon what is on the separator, so that it doesn't escape outside. So that is what we have demonstrated here. And you can see 50 cycles, 800, usually 200 is, or 170 is for the conventional battery material, and I'm talking about 800 with a very good stability. We tested up to 50 cycles, but the trend seems to go beyond that. Okay, so the energy density will be practically, the energy density you can go up to 2 times, 3 times because you put a lot of carbon as support, but that itself is a good achievement. So recently we also showed up to 300 cycles at high C rates, means higher charge discharge capacity. That means it is a real demonstration for a practical application of electric car, because when you drive very fast, it is around 1 C rate, and I get 400, which is double that of conventional lithium battery. That means instead of 200, I can travel 400 kilometers, which is a very big driving range. So these are the things what we are working on now at lower TRL levels to improve the lithium sulfur battery, and then maybe next we'll go to the bigger scale. So I have another 25 minutes, maybe in 15 minutes I'll finish my talk. High power nanomaterials alternate to lithium-ion batteries. These are called supercapacitors. So in supercapacitor, you can see here, the both electrodes, there is no lithium electrode here. There is no lithium cobalt oxide, lithium titanate. This side is carbon, this side is carbon. Okay, that means that it is a capacitor. Capacitor always have, if you recall your high school physics, it is a 2 metal plates with a dielectric in between that one. When you apply voltage, the voltage gets accumulated on the electrodes, and that is the voltage, and capacitance. That gives the capacitance on this charge. So the rule is that half CV square, and how much voltage you can sustain on a capacitor, maybe it's 2 or 3 volts or 4 volts, and what is the capacitance in the terms of farads, and that CV square, C is the capacitance and V is the voltage square, then that is the energy density. So in supercapacitors, why it is called super? in normal capacitors, what we know, what we use in our printed circuit electronic boards, they're all in microfarads or maximum farads. But in supercapacitor, I'm talking about hundreds of farads, thousands of farads. So once the farad, that is capacity C, increases, the energy density increases. You cannot use small capacitors in an electric vehicle, although they are storage devices, because energy density is so small. Even I have 1,000 or 3,000 farad capacitor, supercapacitor, my energy density is still 10 times smaller than the electric lithium-ion battery, because the ions and electric charges are sitting on the surface, but very fast. When I charge a supercapacitor, because I'm not intercalating lithium into any material, like in the case of graphite or lithium and phosphate. Here, I'm just putting the charges on the surface-based phenomena. So, very fast to charge and very fast to discharge, because it's only surface-based. But I need nanomaterials, because for a given geometric surface area, if the surface area of your plate, one electrode is 1 square centimeter, if I use nanoporous carbon, I can increase the surface area, effective surface so huge, because nanoporous, rough surface, then my capacitance is epsilon A by D. A is the area of the electrode and D is the distance between the electrodes. So when I increase the area, my capacitance will increase. If my capacitance will increase, my energy E is equal to half CV square, that also will increase. So essentially, I will increase the energy density, but there is limit. In a pure charge-based supercapacitor, you can go 1/10 of a lithium-ion battery. That means I can use the supercapacitor for my car, and I can travel 10 kilometers instead of 100 kilometers with a lithium-ion battery. But I can charge my car in seconds or minutes instead of hours in the battery, because battery needs a lot of time for the diffusion to take place into the bulk material, lithiation and delithiation. Here, there is nothing like lithiation, delithiation, just sitting on the electrodes. Okay, so, but I don't want to have my car with supercapacitor power, because every 10 kilometers, even it is seconds, I cannot plug in and then charge it. But if it is a public transport system, like bus, and every few kilometers, like 5 kilometers, the bus stop comes, and by the time people get in and get out of the bus, passengers, this will go and then touch the cable at the electric bus station, and then it gets charged and then come down. So that means that every bus station, without wasting time, I can charge my bus. Then all public transport, all your buses, city buses or trams or even auto rickshaws, they can do this job, and they are the main contributor to the pollution. And you don't need to think of lithium, and it's the porous carbon. The carbon can be made by any kind of material, you burn it. Usually activated carbon is made from the coconut carbon, and coconut shells, you burn it in nitrogen atmosphere, you get carbon. You burn any of the material, you get carbon. Sugar, when you burn it, it becomes caramel, and then ultimately it's carbon. And if you leave for a longer time, and it becomes carbon dioxide. So any material which has got carbohydrate or hydrocarbon, then carbohydrate means sugar, hydrocarbon means oil. They get converted into carbon in controlled way. You should not expose to oxygen, and you burn it. So this is the difference. A supercapacitor has got very high power. That means its energy density, it can store small energy like this water, small amount of water, but it can pour very fast. You can see, deliver, that is a power. But a battery, like lithium-ion battery, it can store a lot of energy, a lot of water here, but it cannot pour like this one. It can only pour slowly. That means it has long distance, but you cannot drive more than 100 kilometers. But I can use supercapacitor and use for a race car. Okay, it will go 200, 300 kilometers per hour. So it's again, my student, he shows supercapacitor is like a small 100-meter race, where the guy has to put all his energy and run for this 100 meters starting from the beginning. Whereas here, lithium-ion battery is like a long race where people have to run slowly, but they run with lots of stamina for 10 kilometers or so. So I already told you that public transport is wonderful for this one. And in supercapacitor, you have an electrolyte, and then You have positive carbon electrode, porous. This is porous, so that more number of charges can sit. And negative electrode, more number of charges, negative charges can sit here. And C is equal to Q by V. And energy is equal to half CV square. So that is very well established. And people, you can see Switzerland, China, Poland, all these countries, they use public transport with a supercapacitor powered, because cars usually we don't think of this. And material development, again carbon. I should have carbon with huge specific surface area so that I can store a lot of charge on that one. So we make jute-based carbon, which is graphene-like. You can see the 2D band of Raman, and then make supercapacitor out of that. And then see on par with, if you can see this cyclic voltammogram, the black one is ARCI material, and red one is YP50, which is a Japanese material benchmark commercial carbon with high surface area used in Maxwell American supercapacitor. So we are better than, the area under curve is the capacitance. We are better than even YP50, that is a commercial material. So we demonstrate this and then showcase that at several levels, whether it's energy or power, we're on par with the imported ones. And we show at small coin cell level our demonstration. Let's see, RCI's lighting with the supercapacitor using this jute-based carbon. And we also have other materials like coconut carbon. We can make use of that one. And then we're working with some company to make use of this coconut-based carbon, but converting it to a huge surface area by some CO2 activation. It's called activation. And we also have, most important is HPCL, is a public sector oil company, HP. Your HP petrol bunks are there. So they are oil refineries. They have a lot of byproduct is called petroleum coke, pet coke it's called. And pet coke contains a lot of sulfur, and a lot of small scale industries like cement and steel industry, they use pet coke as a fuel, but a lot of sulfur dioxide comes out as a toxin. So it is, in fact, import is banned, but within the country we have 14 million tons of petroleum coke generated every year, and many of these industries burn it, and then we are contributor to a lot of pollution. But if I use petroleum coke, which has 90% of the metal is carbon, here it's only coconut. If you take, you only get 10 to 15 to 20% of the actual carbon activated high surface carbon, whereas here you can extract up to 7%, even UHA the carbon. So now we are working with HPCL as funded as 1 crore to make this material into the supercapacitor grade, and we established a fabrication line together with HPCL at ARCI, and all this equipment to make the battery supercapacitor cells. You can see here jelly rolls made, carbon coated on the aluminum foils, and then it runs. You can see here this cathode and anode, negative and positive electrode with a separator running the white one, and then rolling it in the form of huge jelly rolls, and then finally you flatten the both sides and then put it in a can, and then finally you make a cell. And now I have a Maxwell device made with YP50 is the blue one, and ARCI is the green one. We are on par with the size and its capabilities. You can see ARCI and commercial are very close, both in the form of charge discharge and energy density, all these. And then it is because it's a technology of the laser welding. Here, the laser welding of this and flattening, this is very critical engineering aspect. I was showing, jumping to the product side is the engineering gap in my first slide, TRL slide. So that gap is crossed here in ARCI because of these facilities. Although we made material and scaled it up and then make a jelly roll, even here to here also it is a big challenge. So we crossed all over, and then today probably it is the first device of 1200 farad on par with 1200 farad imported one, and we are same with the benchmark one, and we're going to upscale, and more number of super caps will come, and we're going to demonstrate a bicycle with this soon with our own supercapacitor. Earlier we already demonstrated with the imported ones. Now we're going to do our own super caps, and probably they're also good for this bicycle. Earlier we demonstrated in 2017 packed with Maxwell super caps, and now that I showed our super cap, then we can use this super cap and then do the same thing. So it's a parallel work. One, you demonstrate and show the capability that you can may have a bicycle without batteries and only supercap. And other side, you make the supercap on your own material, like pet coke based. And then these supercaps, you put it and then demonstrate. That's what in next few months we're going to do, and go for the higher scale and finally demonstrate for a bigger electric vehicle. And we are also looking for a lead acid battery driven auto rickshaw, which is very common, but lead acid battery gets abused very fast whenever you have speed breakers or the like a bridge. If you want to fly over, if you want to climb on, many of the autos cannot climb flyovers. They go only on the service roads, in the bottom roads, because climbing is difficult, especially if you have lead acid electric vehicles. But if you have a super cap combined in a hybrid mode, whenever you need very high power, that means you want to very quick power energy you want for you to climb for a few minutes, or a speed breaker came, it stopped, but when you want to start again, you need to accelerate. But acceleration is very high currents you're drawing, and the battery cannot give high currents. It gets abused, and your 3 years battery life will come to 6 months, and your lead acid battery will die. So supercaps can also assist in those supporting those normal batteries, whether it's lithium-ion or lead acid, so that they don't get unnecessarily abused whenever there is a high demand of energy, whether it's the speed breakers or the climbing the ramps. So these are our excellent team of people these are all actually our scientists and students. This guy is not a driver, he's my senior scientist. This guy recently finished PhD from IIT. And then so all these are our members, right? So excellent team we have. And sometimes for the hard work, we get small token of appreciation. You can see Professor C.N.R. Rao, who was Bharat Ratna, who received a few years back, along with Sachin Tendulkar time. And T.N. Rao receiving from C.N.R. Rao this at Bangalore, India. And we both are from Banaras Hindu University Chemistry Department. That is another proud moment to share. And thank you so much. And I acknowledge scientists, engineers, technical staff, students, were all contributed directly, and then funding from HPCL, NSTL, and of course we are DST, so DST gives use fundings, and industries also are in collaboration, like Innomet, who makes powders and help us to scale it up. And last but not least, in the pandemic of 3-4 months, there's a need to break the chain to protect the public health. And UV is again UVC, that is a shorter wavelength, 254 nanometer UVC, and this wavelength of light, which is again nanometer, disinfect the bacteria or virus by rupturing its DNA and RNA so that it cannot replicate. So we cannot use on human bodies to disinfect, because they also break our cells. So we should be very careful, but they can be used for disinfectant, either in the form of, you can see this almirah, you can keep all your things inside. Of course, you should not expose, and you close it and then switch on the light, like this case. And then after a few minutes, you take it out, your materials, whether it is a bag or whether it's a cloth or whether your utensils or fruits or vegetables, they get cleaned in a few minutes. And here is a trolley in the public healthcare system. There's a hospital or your room or a conference room or classroom. You can disinfect. You run for 10-15 minutes when no one is there with this protective cloth, and then it gets disinfected. And in airports is more contamination, because a lot of baggage will go and through the X-ray check, but X-ray cannot kill the bacteria or virus. So now we have UV scanners before or after the X-ray scanner, so that is also developed with some Vahan. All these companies, here it's Mekin, here is a Vahan, Delhi based. Now this is already there and then in commercial use. And very recently, I just signed, when in between I stopped to sign the form, and then we are developing copper-based paints. Copper kills bacteria and virus, COVID especially. And the paints consisting, is a mineral paint consisting of inorganic binders and the copper. And the Innomet materials, they make a lot of powder for other application, powder metallurgy application. We take that powder and then make in the form of paint. And that paint showed excellent properties for the bacterial killing, already tested in ESIC. And now I signed that form to send this material to CCMB for the actual COVID testing. So if we disinfect COVID, we'll have another fourth product, that is a paint, copper-based, for the disinfection of COVID, so that all your classrooms and conference halls or hospital rooms and all, until 6 feet, 7 feet, you coat it with copper paint, where people will touch, even some patient touches, and it gets disinfected in 10-15 minutes. So by the time probability of next patient comes, and you get disinfected, and your environment also clean. So a lot of things are happening, and we have another project with mask, self-disinfecting mask, where we want to coat nano copper and silver and zinc oxide, so that you can use for longer time, especially for the public healthcare workers, where they cannot change the mask frequently. So with all this, the bottom line is that on National Technology Day, they were asking me during the pandemic itself, on May 11th, we were already in peak pandemic. I mentioned, that came into my mind, I wrote to this Nano TV when they asked, technology should be society, time, and nationally relevant and nation specific. So we should do technologies for our own prosperity and the healthcare, and technology related to public healthcare is the need of the hour at this time of pandemic, and these are the technologies to meet this one. So with this bottom line, I complete it. I think I am in time. Thank you so much. I am ready to answer your questions. Over to organizers.
So thank you, sir. Thank you very much, sir. Any questions from audience? Yes, please. If you have any questions, please ask. Anybody has any doubts regarding the presentation or anything you want to share with the sir? You can talk.
You have to unmute your
yes, unmute your microphone and then talk to him, please. Anybody has any clarification? We are fortunate enough to have Dr. Tata NARSINGA with us. He is a scientist G rank, heading ARCI as Associate Director. Yeah, please. This is a very good time to share your doubts and then clarify, so that you'll be enriched with the knowledge.
Anyway, so if you don't have questions, you can also write email any. I can also answer.
Yes.
No problem.
I will be sharing his email ID, so you can also post some questions and get clarified from him.
So you can see my email ID. It is tata@arci.res.in, and you can see on our website, ARCI website, my email ID and my profile also. Okay. Thank you so much. So if there are no more questions, can I leave now?
Yeah, 1 second, sir. 1 second. I thank Dr. Tata NARSINGA Garu for accepting our invitation and sparing his valuable time to come online because of his heavy schedule to share his expertise and research to all of us. Thank you so much, sir, for giving insight about the importance of batteries and the importance in day-to-day life of the electric car and everything. He's a person of down-to-earth personality. Because of him, you can see him, and though he's a scientist G rank, he has clearly explained the importance of the research and in the area of his research. And I hope all of you have gained the knowledge in this particular area of concern. Now, thank you, sir. Thank you very much, sir. Thank you for sparing your valuable time, sir.
Okay, I am checking out, signing off. Thank you.
Hello. Yes. Now we have another scientist G, Dr. R.VIJAY from the same institute ARCI. Okay. Now, madam, hello.
Sir.
Hello. Can you introduce SARS to audience? Sir, joined.
Yes, sir.
Can you share your presentation first slide, sir?
How do I share this here?
Present now is there, sir, on the right side. Just click present now.
Okay. 1 second.
Just click entire screen. First option.
Okay.
Then you will have one box, sir. In that again, small box will come. Click
that is share, right?
Yes, click that box. You'll get share will be enlightened. Share will be highlighted.
Yeah.
Then click the share, sir.
Yeah.
Yes. Now your presentation will come to us. Yes, sir. Now you go to the slideshow and from current slide full screen, sir.
Okay.
Yes, sir. It's
Could you able
visible,
to?
sir.
Yeah.
Yes,
Could you able to see that?
Yes, sir. It's visible, sir.
Yes.
Thank you, sir. Thank you. Now, Madam will introduce you to the participants, sir.
Good morning, sir. Dr. Vijay Ravula has done his MTech and BTech from NIT Warangal and PhD from IIT Chennai. As a head of Nanomaterials Division, Sir is superheading the programs for development of lead-free copper alloys for bimetallic bearings, silica aerogels, electrode materials for lithium-ion batteries for cars, supercapacitors, nano oxide dispersion, strengthened steels for clad tubes of fast breeder reactors, plates for fusion reactors, and blades for steam and gas turbines, copper CNT and aluminum CNT composites, transition metal sulfides as additive to lubricants and catalysts in petrochemical industry, materials for photocatalytic hydrogen generation from water, and large-scale production of nano powders. Sir has initiated new activities on development of biodegradable implants and powders for additive manufacturing. His current field of research interests include nanomaterials, high kinetic processing, oxide dispersion, strengthened steels, lithium-ion battery materials, supercapacitors, biomaterials, additive manufacturing, and hydrogen storage materials. Sir's award, some of the awards include Fellow of Telangana Academy of Sciences in recognition of his contributions to science and technology from Telangana Academy of Sciences in 2018, FTCCI Excellence Award in 2016 for individual achievement in science and engineering from Federation of Telangana Chamber of Commerce and Industry, Engineer of the Year 2007 award from Andhra Pradesh State Government and Institution of Engineers, Hyderabad Center. Sir has 2 patents already and applied for 5 more, and 33 paper publications and 2 papers in international journals. And Sir is a life member of Telangana Academy of Sciences, Metallurgy Association of India, Institute of Engineers, Hyderabad chapter, Institute of Metals. Sir is guiding 1 PhD and 2 are already finished. And MTech, Sir has guided 12 students. We welcome you, Sir, for today's session.
Yeah, good morning to you all, and thank you, ma'am, for your kind words and for my introduction. Yeah, I will. This is the topic I'll be. Giving you some of the flavors because 1.5 hours is a long time, but then covering different things. Maybe each one is a topic by itself. So probably I will be going through the things, and then if you have any doubts or anything, we can have a detailed discussions afterwards. Yeah, and yes, let me introduce you to the my division. It's a Center for Nanomaterials, and the major activities are the large-scale nano powder production, both by chemical processes and then physical processes. And the technologies developed, one is nano silver based technologies both for water purification and antibacterial, antimicrobial and self-cleaning textiles. In fact, nano TiO2 also. and silica aerogels for the insulation sheets. These top three, we have already transferred this technology. And electrode materials for lithium-ion batteries and supercapacitors, you have been already listened to the lecture by my boss, Dr. Tata Narsinga Rao. And of course, 2D, two-dimension graphene-like sheets of moly disulfide and tungsten disulfides, essentially used as a catalyst in petrochemical industries and as well as a additive for the lubricants. And nano aluminum powder for propellant additive and tungsten jet vents for missiles. This also in the advanced stage of technology transfer, and ODS steels for the nuclear reactors and then steam turbines. Nano boron powders, and we have also received Technology Day Award in 2016 from President of India for the successful development and transfer of technology for our textiles, antimicrobial textiles, and we have got the best award for our stall in Bangalore Nano. And of course, you have seen that we've got Dr.N Rao received award. We have got a Nano award for our activities and all. And we have all collaborators, both national and internationals. We have Institute of Plasma Research, then we have public sectors, BHEL, HPCL, then Department of Atomic Energy and private industries like Resil, Hulical, and bimetal bearings and DRDO. I mean, all those things we have been working on it. And this is, I would like to acknowledge, and then my group at my division, set up on nanomaterials, both scientists, students, and technical staff all together. And this is the work we have been able to do it. And yeah, and of course, collaborators, basically IGCAR, NMC, Vidani, BHEL, and TMRL, what we have been working on it. Yeah, and yes, and then I will start with the strengthening, oxide dispersion strengthened steels. So when you say that the strengthening of any material comes from grain refinement, one is for the, that's what famous Hall-Pitch relationship is there. And if you do cold work, and if you put a lot of strain in the material, it also the strength goes up. And of course, but solid solution hardening, you can see that the carbon or any other alloys like chromium or tungsten or moly or any other material, you can put it. And you can always see that precipitation hardening also you can do it by precipitating carbides, nitrides, and then intermetallics like Na3Al or Ti3Al in the superalloys. That's what the strength comes from for the superalloys. And dispersion strengthening, where you put oxides. So when you look at it, the overall strength is the intrinsic strength of the material plus some additives, additional strength from the solid solution, then the strain, then precipitation strengthening, then dispersion strengthening. So that's why it's all comes into these things. So basically what we are looking at it is we are going to have a typical things like oxide dispersion strengthening along with the grain refinement. We could able to generate the materials. And you can always see that evolution of the steels coming from, I'm just taking up an example of a 9 chrome material. So we can say that people in 1960 to 70s first generation steels where you have only solid solutions and then moly, vanadium and niobium are used. And then when you go into the second generation, they also used boron. They added boron and also tungsten to that. And the third generation, they also added tantalum. And then because they have gone for the solid solution to the precipitation strengthening, and then going to the 95 to 2005, people are okay in fourth generation. And along with the precipitation to the oxides, the dispersion. So that's why the strength goes up. If you compare the strength and then the operating temperatures, the strength levels from the 0 generation to the 4th generation, the strength levels have gone up almost 5 times or 6 times. And then including the operating temperatures also have gone up by around 100-150 degrees centigrade. So that's what the overall development going on around the world. And if you look at the clad tubes of the fast breeder reactor, let me tell you, we have a nuclear reactors where uranium oxide is the fuel, but unfortunately uranium oxide is not available in India, and then we have to import these uranium oxides, even though, and because of this limitation, even though the limitation of the supply of the fuel, the nuclear power plants are not running to the full capacity. They are only running at for 50% or 60% of their capacity. But in India, we have a lot of thorium available. Thorium is available, but that's not used for the conventional nuclear reactors. So what is happening is our IGCAR, Indira Gandhi Center for Atomic Research, they worked on developing this fast breeder technology, where plutonium is the fuel, and that is bred. That is bred from the thorium. So thorium, when you look at it in the things, when you look at it, this is a typical cross section of the fuel pins. This is the fuel tube, and then in which the fuel is made into a tablet, and then put into that, and then you make it, and then that's called the pin, and then around 10,000 tubes are aligned, and then this is the plutonium oxide is the fuel, and around that thoria is kept, and then the thoria converts into plutonium, and then plutonium is used as a fuel. So then we have a full self-sustenance, and we don't have to depend on either country. And then this is a possible technology is developed by IGCAR. But unfortunately, what is happening is this, as you said, that the target burned up. So the 100 gigawatt days per ton of the material, and then the neutron dose is 85 dPa it has to withstand. But what is happening to the problem is conventional steels, when they use it, and you have a void swelling, and you also have a radiation creep, and helium embrittlement, increase in ductile to brittle transition temperature. So that's why the material swells, and then there is a lot of compressive forces are generated, and then material fails before it is used as a before the fuel life is realized. So that's why what is a material selection? You should have a high swelling resistance and adequate end life creep strength and ductility, because it should not break, because handling of this radioactive material, and at the same time the material should be less active material, active elements, so that this material should not become a radioactive, and then disposal of this material is also a big problem. And then compatibility, because this is all used as a sodium cooled. So liquid sodium is used as a liquid, as a material to extract the heat generated by this nuclear reaction, and of course corrosion resistance, and then other things to be there. So that's all in the fast breeder reactors, and then coming back to the fusion reactors, India is a partner to the International Union on the development of the fusion reactors, and where we have to have these blanket plates and then diverter plates, which they also get the radioactive exposure, radiation exposure, and then and also the temperatures, high temperatures are there, so the materials have to be developed to withstand to these things. So that's why high temperature strength, high swelling resistance, and lower accumulation damage. So that means that the material should not become radioactive, but anyhow it will become radioactive, but then the life should be, activation life should be as minimum as possible. So that's why reduced activation ferritic martensitic steels are recommended for this activity. And coming back to the thermal power plants, presently our plants which are operating at around 550 degrees centigrade, and then look at it, the efficiency is only around 41%. But if you operate around 700 degrees centigrade, you can go to around 46%, or 700, 715 degrees, 46% efficiency, and then thereby you can realize more energy from the burning of the coal plants. But the problem is, as you increase, if you want to operate at higher temperatures, the pressure also goes up. And if you look at it at 540 degrees centigrade, which is a subcritical, and coming back to the supercritical, where it is 28 MPa is the pressure, 280 bar, and if you go to the 760 degrees centigrade, around 350 bar is the pressure, which is the steam pressure, which will be developed, and that goes into the turbine. So whole material, everything, it needs to withstand to that kind of stresses, and that kind of life, around 1 lakh hours should be the life, both in terms of in terms of creep and in terms of fatigue life. And so when you're looking at it, is conventionally iron, chromium steels are being used at even up to 600 degrees centigrade. But beyond 600 degrees centigrade, there is no material available there. People are using it. If you go to 700, you are straight away going into the nickel-based LS. If you look at this graph, this is a relative material cost with steel, and then allowable temperature, and then there is this red gap. So there is no material available, but people have to use nickel-based, where the cost goes up by 50 times the steel cost. And so when we develop this ODS ferritic martensitic or ODS austenitic steels, so the cost will be here, and then that can be used in terms of turbine blades in the thermal power plants applications. So in this regard, we have been developing those materials. And why oxide dispersion? When you look at it, the temperature and the neutron dose. So conventional austenitic steels, high active elements, and then they also get void swelling with this. And ferritic martensitic steels, they can take higher dosage, but the operating temperature is less. But when we put oxide dispersion, then they act as a sinks for the neutrons, and they don't allow the knocking of the elements in the material. And so it can take higher neutron dose, and then as well as at higher temperatures. And coming to the why, on some of the literature review on that, how oxides dispersion is happening. So when you have an oxide, yttria is very, very very much used in this dispersion. And so when you want to refine the yttria oxide particles, people tried with the different elements, addition of things, and then they found that the titanium is the one which will refine the oxide particles into the fine stage, and then forming this kind of an oxides, Y2Ti2O7 and Y2Ti2O5 particles. So one is finer, is Y2Ti2O7. People always look for formation of Y2Ti2O7 particles, and then you need to have an atomic ratio you need to maintain, or the weight ratio you need to maintain that. And then when you're looking at it, is different. When you're coming to the lower, this is a particle size, and then Y by Ta ratio. And if you maintain it around 0.5 or to the 1, then the final size will be finer and finer. And when we are looking at, this is a concentration 0.35 and 0.28%, it comes to around 0.75. So that's why you can get a very fine particles. And that's what. And then finally, what is happening? What is the function of the oxide particles? See, they always, when you are putting a stress, and then there is a lot of dislocations will be generated, and then these dislocations will pile up or will move, and thereby the material will break, will fracture if there is a density is very high. So when you have a finely uniformly distributed oxide particles, and then this is a typical dislocation loop, and then they stop these dislocations passing, and thereby you need to put some more amount of energy or more amount of force or stress to move those dislocations. So that's why the strength goes up. And typically when you're looking at the right side, this graph, this is a typical 9 chrome steel, the strength levels, and then if you put oxides, the strength levels have gone up. And similarly 12 chrome and then 14 chrome, the strength levels are going up from the room temperature to even to the higher temperature. So that is the effect of fine dispersoids. That's the science behind it. And even the creep and fatigue behavior goes up. So typically if you see that the stress levels for a different time levels, and the 9 chrome and then ODS 9 chrome, you can see that there is a lot of jump. And similarly to the even the fatigue life also, 9 chrome to the ODS, so the stress is goes up like anything, and then it can take the number of cycles also more. So that's an advantage. So on that we have embarked on a major program on developing of these materials. And this is a typical process lead. We have an inert gas atomizer where we can produce our own alloy powders, and then we buy yttria oxide, nano yttria oxide are available in the market. So how do we disperse? The dispersion process is by high energy ball milling. We can see this picture, and then the powders are to be, once we disperse these powders, dispersed powders are to be consolidated to be used as a material. Then once but the conventional consolidation process, like press and sinter, like any powder metallurgy process, doesn't work, because this powder, because it has gone through a lot of milling collisions in a mechanical milling process, so they accumulate a lot of strain. So once we have a strain in that, then when you are pressing it in a room temperature, then because of the strain in that, then they will have a spring back. So the green density what you get in this material will be very low. And then when you put the sintering, so you will not get a good density. The density is only around 80%, and the remaining will be the porosity. So that's why these materials are to be hot worked. So in this case, how do we do hot work it? Because we do the hot extrusion process or heating process. So in this, so then when you are hot working it, you cannot expose this material to the air at the temperature because it gets oxidized. So that's why the powders are filled in the can. These are the cans, and then filled in the pneumatic vibrator so that you get a good tap density. And these are all, then once the cans are connected to a vacuum degassing facility, which is heated at around 400 450 degrees centigrade, and then where the absorbed gases on the surface of the powder particles, they come up and then they will be sealed. These cans are sealed and under vacuum. And these cans are made it into the billets by hot extrusion, by upset forging in a closed die, and where you get at a temperature. So thereby you get around 98% density. And these billets are hot extruded with a different extrusion ratios to get the sizes, as you said, that 16 mm to 40 mm or whatever may be the size you get it. And then these rods, extruded rods, you use it for making it heat treatment, characterization, or conversion into different components. That's what we do it. And this is what extruded rods, we get 40 mm rod. And then when you do the pilgering, you get a clad tube for the fast breeder reactor. Then you do the hot rolling, you get a plates for the fusion reactor. And then you do the closed die forging, you get a blade for the turbine, steam turbines. So this is what the turbines blades we made it for the 500 megawatt first stage turbine. And we also have a state-of-the-art facility for the manufacture of the powders. And this is what by inert gas atomizer. It has got in 3 compartments. The top portion, you can see that right, which is a melting furnace, induction melting furnace, where in this crucible you put your material, and then you melt it. And in the bottom of that is a atomization die, where you have a metal flowing nozzle and as well as high pressure gas supply, and this gas will hit the molten metal stream which is coming out through the nozzle, and thereby the material is made into the spherical the powders. They get immediately, because you have a high gas velocity and you have a buoyancy forces acting on the particles, so that's why that make it into a spherical shape. Unlike an water atomizer, because the cooling rates are very fast. Atomization gives you an irregular powders, whereas gas atomization gives you very good spherical powders. And these spherical powders are very good for the because they give you a lot of flowability of the material. So we made the different, our capacities, temperature is 1850 degrees centigrade, gas pressure we can vary from 30 to 80 bar, and 10 kg is the melt capacity, and we can use helium, nitrogen and argon gases for making these powders. And because we use this, is oxygen content is a very, very critical in all these high-end applications. And we made 9 chrome, all chromium steels, and SS stainless steel powders, 718 and iron aluminates, we made it. And we also subsequently, the mechanical milling, we use it as a JAWS horizontal high energy ball mill. And the typical thing is, when you're looking at the mechanical milling, you have a it's a repeated fracture and welding process taking place because of the ball to ball collisions, and then collisions between the ball and then the vessel of a mill. And what happens is, everything depends upon the relative velocity of the balls being generated. And if you typically looking at it, is an attritor conventional, you can compare a material, same material which is milled in an attritor. It takes 40 hours to give you a particle size and the cell size, and then but the same thing takes only 4 hours. So that means the time required for the milling when you use this mill is very, very low. The reason is because it's got a very high kinetic velocity it generates, greater than 14 meters per second. And that's why the energy input is half mv square. So you can imagine the kinetic energy generated is very huge. And then the short process time and low contamination, because milling is a very dirty process. If you keep milling that, there is a lot of wear and tear on the balls and then vials. And then the longer the duration of the milling, there are higher the chances of the contamination of this material, the ball material or the vial material coming into the your powder. And if you look at it, whereas typical things, high energy ball mills like planetary mill gives you only 5 meters per second, attritor gives you 4, and conventional ball mills gives you less than 5 meters per second, whereas this horizontal ball mill gives you 14 meters per second. And the beauty is, see, if you look at it in our mill, there are no dead zones. It is designed such that at any point of time, so the balls, powders are on the motion always. Unlike any ball mill, there is always a dead zone. All the ball mass is on the one side of it. So that's why these are all the advantages of this mill, and then we made use of it, and then we produced these powders. And these are all the starting powders. We can see that 9 chrome steel powder and then 18 chrome steel powders, and typical chemical composition is given here, and then the size fraction CV analysis are given here, which is all produced. And these are the materials we produced in house and then used it. And this nanoytria what we have purchased, and then particle size of around 35 nanometers, and surface area is around 31 square meters per gram. And when we put that milled it, we have seen ideally the reaction is to form this, as I mentioned to you, Y2TA207 particles are to be formed. Then this ytria should be should dissolve in the matrix and should not be there. Should completely dissociate and then dissolve. So that is optimum milling time, where we have seen that in 1 hour mill time, we can clearly see that white spots are typically Y2O3 still remain, and even at 3 hours they still remain. And when we go to the 6 hours milling, you don't find any of those ytria particles. So that means they remained as a dissolved in the material or remained as an atomic cluster, because they lost their chemical, the structure of this compound. So they are remained as atoms in the material. So that's why 6 hours is an optimized milling time for the dispersion of the ytria particles, and then went ahead with the consolidation process. In the consolidation, consolidated extruded rod, when we look at the typical microstructure, this is an EBSD grain boundary map, and where you could get the grain size distribution of around 630 nanometers, we could be able to get the very fine grain. And then average dispersoids, you can see that these are all the particles uniformly finer and then uniformly distributed, and their size is around average size is around 5 nanometers, and then their number density is around 10 power 23 per meter cube, which is equivalent to an Avogadro number. So that's very huge, and volume fraction is very small. So because what happens is, if you are increasing the volume fraction, the material will become brittle. It becomes like a ceramic. So the ductility comes down. So that's why we need to have an optimum content of these oxide particles. So finer the particles, more the number, and even you can get it with a less volume fraction. That's what we could able to achieve. And even if you look at the 18 chrome, and typically this is an EBSD grain boundary map, and you can see that grain size distribution. So grain size is around 370 nanometers, and the dispersoid size, oxide size is around 4. And if you look at it, the typical particles, what is the structure of the particles, you could able to see that this is a Y2TA207, and this is a selected area diffraction image. And then we can always see that they are all KS relationship is maintained, and there is a orientation between the matrix and then particles. So that's why they're not dispersed. Generally, dispersoids will not have any orientation, but here they have a orientation. So that means they have actually a precipitation of an oxide, not as an intermetallic, not as any of the carbides or nitrides precipitated, but oxide being precipitated in this material. Right. And that's why they are all finer. And coming to the properties, we can always see that at a different temperature, the yield strength. You can see that our 4 hour and 9 chrome sample, we can able to see that around 300 of course, any material loses the strength when you are doing it at higher temperatures. And if you look at it around 700 degrees, which is all the operating temperature for the fast breeder reactor or the steam turbine, they're around 300 MPa. So the material what we need is only 100 MPa. But both 9 chrome and then 18 chrome gave around 300 MPa strength at 700 degrees centigrade. And we have also done the modeling, because when you see that as I mentioned to you, it's all the linear, it's also summation of the individual strengthening components like matrix strength or Hall pitch strength or the dispersion strength. But we could able to find out at room temperature that they don't follow linear summation, but then they always follow the root sum square method, and you could able to see that our experimental value and the calculated model values are matching with that. And these are all the papers published in Material Science and Engineering, and then or Metrans A papers, or even ACTA paper. They are all published. And we could able to predict, and then what could be my grain size, and then what could be my dispersoid size, so that I should get some kind of a strength. The beauty is, see, it's all the two strengthening mechanisms are occurring here. One is the grain size strengthening, and then the other is the dispersion strengthening. So generally, we can always have a nano-grained structure by working up the material, either for the uniaxial, equichannel processing. So you work on, you roll it, and then you do it, and then you refine the grains. But the problem is, as soon as you expose to the higher temperatures, there is a grain growth, and as the grain grows, the strength comes down. But here is, you are working on the material during the hot extrusion, so that's why you are getting very fine grained structure, and also you'll have a dispersoids on the grain boundary or within the grain, and these dispersoids, they pin the grain growth. So that is an advantage. Even at an exposure to the higher temperatures, they don't, these fine dispersoids which are available on the grain boundary or within the grain, they don't allow the grain to grow. So that's why this fine grain structure is still gives you the strength at higher temperatures. So that's the beauty of these materials. And you could always see that, you know, from the extruded rod, a mother tube is made, and then from that clad tube, and this is what we have handed over to the IG car for the practical applications. And then these tubes will be now will be used into this Bhavani, the first commercial fast breeder reactor, which is coming up, which will be commissioned by end of 2021. So where these clad tubes will be used. And this is all turbine blade is also made and given to the BHL, and then they are all testing these blades before it is being used. And based on that, we are also looking at an austenitic, because I was talking to you around 9 chrome, which is as though the strength and all are okay, but the problem is they suffer from the corrosion and then oxidation resistance because of the lower chromium content. So in order to have, if you want to use it at even the gas turbines, where the corrosion and oxidation are the biggest problems, where we can always have an austenitic steels where they have a good oxidation and corrosion resistance. And when we put, but austenitic steels cannot be used beyond 500 degrees centigrade. So when we put an oxide dispersions, then we can, the strength can go up. So that's what we are working on it. These austenitic steels, the future generation steels for the turbine blades. And then other is the aluminites. So many are working on aluminites like iron aluminites and the nickel aluminites or titanium aluminites. But these aluminites are the very brittle materials, even though they are all lighter, because the density is 6.6 grams per cc compared to the superalloys of 8.2. So the around 20-25% reduction in the density, and that will also give you the efficiency of the turbine. So lighter the material, the efficiency goes up. But the problem is that they suffer from the poor ductility. The room temperature ductility is only 4%. But you know that when you going into the nano structured, when you maintain nano materials, the finer the grains, the higher the ductility of the material, and that's what we have employed. And then how do we retain the finer grain size? By dispersing fine oxides. So when we have done that iron Fe3Al material, which is again dispersed oxide, dispersed in this intermetallics, and we have extruded and then made the rods, and you could able to see that different oxide particles are present, and then the strength levels are very high, and even the ductility is very high. We could able to see that. We could able to achieve around 16% ductility at room temperature. You can see that around iron aluminate being developed around the world, and what we have done it is way too far. The ductility around 16%, and that's the combination of the strength and the ductility at room temperature is very high compared to the any time. So first time in the world we made it, and then the Indian patent is filed, and we are generating a complete data for an engineer to use this material in a commercial application, turbine blade, like the data in the sense of creep, fatigue, and then oxidation studies, then creep fatigue interactions, then age hardening. You see, when you expose the material, aging, thermal aging studies, when you expose the material, because these materials are supposed to work for 1 lakh hours at an elevated temperature. So what happens if you keep exposing that material at the temperature? So all these things like complete database we have been generating with an association of NIT Warangal, NML, and even IIT Madras. So that is what on the oxide dispersion strengthened steels. This is one of the verticals of our material development program on these things. And then this iron aluminates also we have been working on for the coating purpose, because people are using it for the nickel chromium or nickel chromium carbide as a materials for the coating in order to have a good oxidation resistance. But they are all expensive material, and when you use these iron aluminates, they also have a good oxidation resistance they exhibit, and they are all cheaper materials because you are not using any nickel or any other element, nickel, vanadium, or any other element there. They are all costly elements, and this is also showing very encouraging results on that. And then still we are working on even high temperature properties, and then cyclic stability, all those things we are working on. So it shows that iron aluminate is a potential candidate for the lightweight high temperature applications, and as well as for the both structural and as well as for the coating applications. This is all it is. And coming to the another advanced processing is, as you said, see, when you make a nano material, nano powder, and if you do the consolidation from the powder, is conventionally used as a press and sinter. So, but when you are exposing to this nano powder for a longer times in the conventional sintering process, but they after coming out from the furnace, they no longer remain as a nano sized or nano grain structure. They are given as a polycrystalline material as conventional, and there is no advantage of using nano powders to make a component by the conventional process. Longer the exposure time at higher temperatures, then there is a grain growth, and then they become like a normal any other conventional material. But then how do we do this? How do we consolidate? So we have to, if you want to consolidate, we have to do it at higher temperatures, but we have to do it at very less time, very quickly. So that's why we need to have a process where the temperature rise is very fast. So something like a heating rate of even 400 Kelvin per minute. 400 Kelvin per minute you can achieve. So that's called a spark plasma sintering. You can see that we have both types, 10 tons and then 100 tons. 10 tons is to do that conventional research, and then 100 tons we can make some components. And this is what the graphite dies, where the material is put in die, and then you have a punches. And when the high current is passed, and you can always see that the die, red hot die, which is actually with the temperature it is undone. That's the picture. And the conventional process is what happens. See, when you have a SPS process, if you look at it, so you pass a current in terms of pulses, very high current, and then because of that current, and then there is a gap between the particle to particle. So that's why that creates a spark. And also there is graphite is a good conductor. So there is also a Joule heating taking place because high current, so I square R is the heat which is generated. So high current, so that's why the temperature rises very fast. And then you simultaneously apply the pressure, and then they get consolidated. And then typically you can see that the various materials, bismuth iron oxide, which is all you can do that, very fine grains you can do that. And then even yttria stabilized zirconia, what you got, you can get a very fine grain structure and good density you can achieve. And even also you can make it as commercial 3D complex shaped nozzles. You can produce all these carbides, xylons, zirconium borides, and then hafnium carbides, all being can be developed using this process. And then you can see the tungsten carbide materials, binderless tungsten. See, sintering of tungsten carbide is a big problem. People use because it need a very high temperatures for the get a good density. So that's why people use as a binder, like a cobalt as a binder, or even the nickel they use as a binder. So they use a liquid phase sintering. So because of the less strength material, so the overall strength of the tungsten carbide goes down. So, but when we use this spark plasma sintering, we don't have to use any binder. We can always use as a tungsten carbide directly and then make these components. And typically, these are all the other materials you can always do, like nozzles, bushers, press stamping punches. Also, all those things you can sputtering targets, even biomedical devices, and then you can functionally graded materials also you can do it on this using this process. So one of that, what are the activities we are doing is we are using as a tungsten plates for the jet vane applications and high entropy alloys, better density at room temperatures, and then because of the higher strength and hardness, because everybody knows now high entropy alloys are the hot topic going on around the world. And again, functionally graded biomaterials as a dental implants with because titanium, zirconium oxide, and then hydroxyapatite functionally graded for the dental implant, and that's what it is doing. And you can always see the tungsten weight balance in the missiles, the missile wings are there. And some of the other materials also, aluminum, silicon, and then other things also for VSSC we have been doing. And even tungsten fiber composites for the plasma placing components in the future when fusion reactors are being developed using this spark plasma sintering process. And typically one of the examples I can tell you is the tungsten plates. We can do it by the spark plasma sintering. So these these jet vanes are needed in the, they're all in the at the bottom at the nozzle of the missile to essentially to guide the missile into the when it takes off, and then to guide the missile, change its direction, and then put it into the proper projection. So what happens is you have a 4 nozzles, four vanes are there, and these are all manipulated to maneuver the gases, the combustion gases coming out from the nozzle. So that gives you the thrust, and then that can change the direction of your missile. But the problem is they need to have a good erosion resistance at temperatures, and then good strength they need to have, even though the time is only 5 to 6 seconds. This is all once it takes off and then puts it in the projection in the direction, then it goes off. So that's only the 5 to 6 seconds it has to withstand. And then we have been interacting with DRDL, and we made around 32 pieces, which we can even see that very fine grained structure, because we put a 1 nano oxide dispersed, nano phase, a different phase we have dispersed, and then that way we could able to get a very fine grained structure, and the strength values are gone up. So if you look at it, the transverse rupture strength and then versus the hardness, if you look at it, see, typically when you look at the tungsten is here, and then ODS oxide dispersion tungsten is here, and any carbide dispersed metal carbide dispersed tungsten is here. But our work is right now over here, so it has got a huge strength, and then as well as hardness it could able to generate. And these are all the conditions what we have done. A tantalum carbide is used, and we could able to get around 1600 to 1650, and then that is much higher. So that's why we have done a lot of experiments and then optimized what is the tantalum carbide content, what we need to have in terms of the density to get a good density and then good hardness of these things. And then we made a lot of pieces and then supplied to DRDL, where the field trials are taking place. And this technology is ready for the transfer. Industry is also interested to take up this technology. And another process is a nano powder large scale production. This is called RF induction plasma. So what happens is, this is all physical process. So what happens is when you start one of the processes is you start with a micron-sized powder particles, and then you start directly vaporize the material because of the high temperature of the plasma. And when you start rapid solidification of those vapors, and then they result into the formation of nano powders. So how do we achieve that? So this is called a radio frequency induction plasma. So the top portion is where you feed the powder, or in the form of wire also, in the form of powder also, this can be fed. And this is the plasma zone where you can get up to 5000 degrees centigrade. So, and then when any material comes into that, then when you have immediately, because of the high temperature, the material becomes vapor, and then that vapor is quenched with by passing an argon gas, and then if you get a metal, and if you pass an oxygen, you get a oxide, and if you pass a nitrogen, you get a nitrate. So this is what you can always play and then get the materials. And these are all pushed by the gas, and then comes into this hopper where you can collect it into the glow box. So different various metals, pure metals, you can do that: silver, aluminum, copper, iron, various materials you can make it. There's around 20 to 75 nanometers. And then oxides, alumina, silica, TaO2, all those things. You can also make carbides like tungsten carbide, silicon carbide, boron carbide. So these are all the things you can do it. Even the nitrates, titanium nitrates, boron nitrates, silicon nitrates, all those powders you can make using this process. So typically, as I was mentioning about it, this is what the thing. Then there is a powder which comes into the plasma zone. Then they become vapor, and then the vapor is quenched with a quench gas. So then rapid solidification takes place, and then they don't. Once they start nucleating as a solid, and then they are all pushed away by the gas. So they don't allow to stay. If they stay, then the particle growth will be there, and then they will be collected over into the different materials. So that's why you can always say that the plasma discharge, hot section, then you have a quench section, then comes to this. So the longer, because when you are passing with the gas, the bigger particles, they settle down over here, and then the finer particles will go into the hopper and then gets collected into the thing. So for anything, the critical thing is you need to play with the metal flow, gas flow, and then the power of the plasma you have to treat, because the residence time is very, very small. So you have to play with these things to get a desired size, and then with a desired size distribution, what you have to get. And typically what we made is an aluminum powder. So what happens is we have nano aluminum powder. Aluminum as such is used as an additive to the solid propellant, and because of the when you reduce the size, then the oxidation kinetics are faster, because the diffusion lengths of the oxygen is smaller, and that's the reason you go to the nano size, then the energy release will be higher. If you can see the thermal characteristics, so if you see that finer the size, so higher the typical temperature, so higher the oxidation rate, and as well as the higher the heat change. If you see that the micron, the black one, is always, it's directly it is melting, it's not even burning. And whereas if you look at it nano sized, it's getting oxidized, it's burning, and then it is releasing the heat, and then that heat can be used in any propellant, so fast. But the problem is, so when you happen is the metal, finer the powders, always they become pyrophoric. Even if you expose to the air, they just they burn, and then they get oxidized. So there is shelf life will be very, very poor. So in order to overcome that, in order to improve the shelf life of the material, what we have done is, typically on any particles, we put we just grew an oxide layer. It's a very thin, so this oxide layer, it should be, once then, in the beauty of aluminum is, once you have an oxide layer, alumina layer forms, it doesn't allow the oxygen to diffuse further. It acts as a barrier for any oxygen to go into the material. So, but the problem is, if the thickness is more, they don't burn. So alumina itself is an act as a resistance for the oxidation of the metal thing. So you need to have a very small thickness, so that the material will not get oxidized when it is kept exposed to the air. But but they start burning even with a small spark. So that's why we have we have optimized a 2 to 3 nanometer sized. You can see that typically 2 to 3 nanometer, very, very fine sized an oxide layer is sufficient to improve the shelf life, to stop it from self-oxidizing, and at the same time burn it when you put a little spark. So, but then our people, our group have done a lot of experiments, and you can see that the thickness of oxide. But at the same time, when you are putting a lot of when you increasing the thickness, obviously the alumina content, Al2O3 content also will increase. So, but then that loses the heat generating capability of the material, right? So the enthalpy comes down of the material. So in order to have a balance, so that's why they put up around different sizes, and you can see that 1 mm as the size comes down, because more amount of surface area, more amount of alumina, even as well as go up to 15 weight% with the 1 mm thickness. So that's why they put it around 200 mm, 200 nanometers of the size, and then maintained around 2 to 3 nanometers. So it's around 8% is an oxide, but still 90% or 85% is a metallic content. So that's why they have worked on with the different techniques and then done that. So this is what I was trying to use. This can be used in any other any missiles as an additive to the propellant, and we have supplied even to the rocket launching vessels, vehicles. Sorry, rocket launching vehicles, and to the VSSC we have supplied, and they will be using it, and then they need a lot, very, very huge quantities, and this is another technology we will be transferring it. If it typically the same oxide barrier coating which is done on the particles, which is packed in the thing, and when you expose they don't burn, but then when you put a small spark, you can see that the whole powder is red hot, it's all burning. So that is a beauty. If you leave it in the air, they don't burn, self-burn. So that's what it is doing it. And then we have field trials are going on and essentially doing with a technology transfer for this nano aluminum powder for the propellant applications. And coming to the other advanced, another processing is an additive manufacturing. So you might have known what is additive manufacturing. You build the components from the model, a 3D model you need it. From that you build the component or any other part by layer you build it. So that's what additive manufacturing. And you always know that 3D printing is always in the market, and then they are making different things. They are all making all plastic things, and then you can see that syringes and then other things are already being manufactured in industry, plastic things. But the metal additive manufacturing is a new thing. People are still right now only working on it. It's not coming into the commercial stage, but we are working on it. So this is the advantage is you can get any near net shaped component or any intricate shapes which is not possible by the conventional machining. So you can avoid machining, and you can avoid wastage of the materials, and you can always have any features which are not possible by any other conventional manufacturing technologies. So that's why additive manufacturing has got its own advantages of that, and where we have been doing it. So the powder, so how do we do that? So you can always do that powder bed fusion. So you'll have a powder bed, and then with the powder is melted in the layer, which as per the 3D model, it's all sectioned, and as per that the powder is melted by the laser, and we can do that. So you can always have a selective laser melting or a direct metal laser sintering. So that means you have a in the one is selective laser melting is you have a powder bed where the powder is filled as a layer. Then the laser moves in the as per the contours given in the drawing, and then they melt, and then that gets welded to the layer below that. And then other is direct metal laser sintering is you have a nozzle in the powder hopper, and then that will be moving along the contours of as per the drawing, and then the laser moves behind it, and then that melts the particle so that it gets welded to the a layer. So that's what you can always do that. You can always electron beam welding. You can do the wire, and then you can build the things. And then you can always have a direct energy deposition powder feed systems or wire feed systems or even the sheet laminations. You can always do that. You can always have an ultrasonic additive manufacturing. These are all the things. What we have in ARCI or is a selective laser printing, laser melting, SLM, powder bed fusion method, and then even DED, powder bed system we also have. And we also have a binder jet system where we can also have a powder, and then they are all brought into the single, they are all in powder particles are integrated with a binder. So the binder, the binder, liquid binder is poured as per the contours given to that, so that they get solidified and then they bind the powder particles together. You get a structure of that, and then that has to be post-processed either through the heat, debinding and then heat to get a good density in that. So we have 3 systems in our ARCI. So conventionally, what is that we are doing it is you do with a design, a model, the particle, the component what you need to have. Then from the model, then you get a machine, and you also have a powder you need to have. So we also have a powder manufacturing facility. And once we have a powder, then from the model, you put it into the machine and you do the manufacture the component. And you can also do the post-processing of the material, because post-processing is very important, because this is a non-equilibrium process, very rapid cooling, quenching taking place, because the cooling rates are because the heating, the material which is being melted is around 100 microns or 50 microns or 40 microns, and then they get cooled very fast. The cooling rates are very high. So that means it's like a quenching process. But then it is also having a repeated heating cooling cycles going on, because you are building by layer whole component. And you need to have definitely need to do the post processing. So you need to have a furnaces, or you need to have if you want to improve the density, you need to have a hot isostatic pressing, you have to do that. Then you will also have a characterization. So all these facilities are available at ARCI. We have been working on and developing many components, many of those things. So what is a powder bed AM? You see, you can always see that you can always see that powder is taken from the powder storage, right? And which is all kept it into inside the build platform and spread using a roller. So this is all the things. So then powder cannot be added during the process. So spreading can only be done in one direction. So that means once you have a powder, then the laser moves it and then they build it. So powder is delivered through hopper from top of the bed. So that's what it moves it, right? And then laser moves it, it builds it. And then this moves, the base, the build chamber moves down. And then so that again, the similar kind of powder is spread in the bed. And then the laser moves as per the contours, and then it can do it. So that's why you can do it. So what is all happening? So what is all our roadmap towards that is we need to have raw material. So that means the availability of the powders for the additive manufacturing. And you can also have, because it's a non-equilibrium process, so the microstructural development is totally different. So the properties what we get from the conventional manufacturing, like a cast and then and then forging, will be totally different than the properties what we achieve by the additive manufacturing. So that means even you have to have a different alloying elements, different systems we need to have for the same kind of material. Then always have a material interaction and formation of melt pool, scanning area, then efficient scan speed, because it's a slow process. If you are producing, taking around 100 hours, 200 hours to make one component, see that ultimately economics decides the success of any technology, right? So if you are taking too long time, then the cost obviously will be higher. So it's not economically viable. So we need to improve all those things. And then you have to select different AM systems for the different components, different things. So we can always see that in system also you can do that. Build chamber size, so different sizes. Then you can also have a different, many components also can be made if you have a large chamber. And then powder handling, because powder should not get oxidized during the processing. And then you can also preheat the powders so that there will not be rapid solidification, you can always avoid the post-processing things. And you can also do that the processing of non-spherical powders, but you can get different composites and then other things you can do that. So you can always see that wide LR range, efficient scanning strategy, and then software. Obviously, you need to have a process simulations involving physical modeling. We have to do that. And then look at going back to the, so we are all working on developing all these aspects in our organization. So we can always say that design for the additive manufacturing, application development, development of specialized powders for AM, and repair and refurbishment, and numerical simulations and indigenization of the technology. So these are all the things we have been working on it. And I'll show you from typically one of the components what we can see. See, you can always see a gas manifold. A gas manifold, this is made conventional manufacturing process, which is of 5 kgs of weight. And when we build, we can remove some of the redundant areas, and then we made it into the new design. And then the weight reduction is by 40%, and then serving the same purpose. So that we could able to save. And then other material also we could complex, say wall block. And conventionally, when you make the block is this way. And when we made by the AM, because of our design flexibility and then manufacturing flexibility, so the material is reduced, and we could able to make this kind of wall blocks with the stainless steels or even aluminum alloys. So we can always see that we will have a design freedom. Then we can also have a part integration. So we can put one part to the other part. Then we can always see that different intricate cooling channels, conventionally not possible to build it, right? And then even lightweighting, we can always do that, like putting into a honeycomb kind of structures, and you can always do the dissimilar welding things. You can do that, and you can also doing that alloy powders. The basic problem is the non-availability of the powders, because all the powders are being supplied by the manufacturers of the equipment only. We have to depend on them with their own chemistry and then particle size. But there is no powder availability. So we have embarked on the powder development indigenously. Right. So one of that is 718 powder. That's in superalloys, IN 718 powder. So what we have seen is we have an atomizer, and the particle size from the atomizer depends upon you can always see that the particle size depends upon the gas pressure. So that means the atomization gas pressure. So higher the gas, the finer the particles, because you will always have a higher the cooling rates and then higher buoyancy forces and higher pressure. We can have it so that the splitting of the stream will be extreme, and also as a gas to metal flow rate you can always have. So higher the gas to metal flow rate, so you have a finer the particles, higher the gas. So we have over a period of time we have generated the data, and then this graph is produced by making different parameters, and we could able to see the main size. Now for any material we can always look at it. What is the condition we need to get the particle size? And typically, if you could able to see that the particle sizes of the powders being produced, we have a big hopper where you get around 33 microns is the size what we got, and in the small hopper we got around 17.5 microns is the size. So and this typically 33 microns goes for the additive manufacturing. And even 718, so these are all the powders. You can see that our ARCI powder and then the commercial powders, and we could able to compare the chemical analysis. It's all comparable to the commercial available, and even the surface roughness has built. So the AM coupons or anything are built to evaluate it, and we could able to see all those things. These are also comparable. And when you're looking at the hardness data with density, we could able to get different, same as a comparable to the, even the hardness also comparable, and the solutionized aged also are comparable to the commercially available powder. So that means we have successfully made the powders for the additive manufacturing, and we have been supplying to the other people also. And we are working with the Mithani in these terms to essentially, because ARCI is a research organization, we cannot, it's not a production unit, and ultimately somebody has to take up this production technology, production of these powders for the supply to the various EM users. So we are working with the Mithani to establish a plant for the production of powders for the additive manufacturing. And what is it? Yeah, and similarly, iron 625, another superalloy powders. This is also produced in our ARCI inbuilt, and then we could always see that composition, it's all matching, and also properties, it's all matching with the conventional powders, and even the oxygen. What we could able to get is our oxygen content is much lower than the commercial powder. So that's why lower the oxygen content, then the higher the purity, and then higher the performance of the materials, especially in these superalloys. And another thing is, as you are aware, our ARCI is also working on fuel cells. And fuel cells essentially is the bipolar plate is the very critical component. And earlier people are using only graphite-based bipolar plates because you need to have a channels for the flow of oxygen on one side, hydrogen on another side, and then oxygen on one side. And that's why when you have a reaction through the membrane, when you have an hydrogen-oxygen reaction, then there is an electricity generated. So that's what the fuel cell works. So, but when you are using a graphite bipolar plate, because of its lower strength, and the thickness has to be very high. So instead of, then the whole system becomes bulky. But when you look at the metals, which is all built by the additive manufacturing, we can able to build these materials with the different, as per the channels flow for the gases, as per the designed channels it could able to produce, and then the thickness can be maintained very small, so that the overall size of the fuel cell will become less. And so you can always see that 80% of total weight and then 45% of the total cost can be reduced when you are using it. And that's what this is all being used in our fuel cells, these plates. And another thing is nozzles. When we beat it, when we make it, you can always see that conformal cooling of this cooling channels, which is not possible by any conventional process. So we can have it. So the efficiency goes up, the life goes up. So that's why these nozzles are made and supplied, and you can always for the usage over here. So that's the beauty of this additive manufacturing. And then another thing is, like I was mentioning about it, the fuel pins in a nuclear reactor. So how do they put it? So that's why they put a bundle, fuel bundle plate, a spacer for the fuel bundle. And this is what it's kind of a ring, so that in each hole there's our fuel pin goes. But when you want to make by the conventional machining, so much of drilling, so much of machining, so much of things with such a thickness of one gap of only 1 mm is maintained between the plates. So wall thickness is only around 0.4 mm. So it's a very, very difficult thing doing by the conventional thing. And with the BARC atomic energy, we made these plates, these spacer plates, and then we have supplied, and there are 37 holes are made into each one, and surface finish is just less than 3 microns, and then these are all supplied to the BRC, and they are been validated by BRC for the usage. And this is another technology we have transferred. And variable thickness converging diverging nozzles, especially in the missile applications or the space launching vehicle applications and all. You can always see, it's all, you cannot have this kind of things into the by the conventional process. So, and we made a 3D model. You can always see that the thickness comes down and then it goes up. over here, because of which has to withstand to the pressures and then other things. So what we can do that we can have a 14 mm converging OD, diverging OD is 26. So we could able to design and then build it with a very less tolerances. And the thickness, when you see that actual dimension is 0.5 and then build dimension 0.64 on the diverging. So such a thin. So the material also we are saving on those things. And another thing is the shock attenuators. So metal, so it's like an honeycomb structure, and when there is anything is there is a shock on the material. So if you want to have a metal, and then when you make a honeycomb, so it will also have a shock. So basically, earlier we are looking at a that people are using as a PU foam and all. Are using it to have a shock, but then that was not working, and it's talked about is a metal honeycomb structure. That's what the DRDL came to us, and stainless steel honeycomb structures we could able to make. So you can see that. So it's only the high density 3.3 milliseconds, low density 1 millisecond. So this is all we made it, and we could able to see that the shock levels it could able to withstand top and then bottom shock levels it could able to withstand, and it can absorb those shocks, and then these are all successfully field trial tested at TATA. Right. Yeah. So these are all some of the things what advanced processing at ARCI have been doing. Thank you.
Thank you, sir. Hello. Thank you, sir.
Yeah.
Dear participants, any questions? Yes, please. Any questions?
Yeah, I would glad to answer questions.
Sir is ready to answer the questions. If you have any queries, please post it or directly unmute your microphone and then ask him. Okay. So I have a question, sir.
Yeah.
You are telling about manufacturing of nozzles.
Yes.
By internal cooling channels.
Yeah.
So how does this channel is prepared, sir?
No, because this when we want to have we do a heat transfer calculation. So what could be the size? What could be the contours of the channel we need to have, and based on that we prepare a 3D model. And then when we are building it, manufacturing it, it's building by the layer by layer. So section by section. So whenever the channel is there, so the powders will not be melted. So it remains as an will be hollow. But around that, the structure will be built. So that it goes continuously, it builds, and then when you make a total thing, then you'll have a hollow channel comes into the system.
Okay. Thank you, sir. Anyone? So if you don't have questions, we can wind up this. Or else, do you have any questions, please? Anyone from audience? Yes, please. So thank you very much, sir.
Yeah, I think probably I finished it. I was too fast. Finished it in.
Yes, sir. Yes, sir.
Yeah.
No problem. No problem. Because you have started early, sir.
Okay.
So that's not a problem.
Right.
So I thank you, Dr. Vijay, for sparing his valuable time to come online and share his expertise and research to all of us. Thank you so much, sir, for enlightening us in powder metallurgy area and its effects, and also especially on additive manufacturing, metal additive manufacturing process, and how to manufacture intricate shapes. And you are clearly explained the process of additive manufacturing, and especially you have throw some light on fuel cells, bipolar plates also. Thank you for sparing your valuable time and joining us. Thank you so much, sir.
Okay, thank you. Right. So I'm leaving now. Yeah.
Yeah. Thank you, sir.
Thank you.
So, dear participants, as sir has started very little bit early, around 11:20 itself. That's the reason why he is leaving the classroom. Okay. So, we'll meet again at 2 o'clock. So, another person from BHL R&D will be joining us. Will be sharing his expertise regarding coatings and also applications of that in the session from 2 to 3:30. We have slight change in the schedule. That's the reason why I'm announcing you. So thank you for so much. Have a great lunch and then come back. Don't sleep. So my sincere advice and request to all of you is, when we are inviting such a great experts of scientists of cadre G, you are supposed to interact with one or two questions. This is my sincere request. Please interact. At least some post questions or repetitions, you can ask something so that they'll be happy. So try to interact so that you can gain knowledge, and also you will be helping others, those who are not asking just now. Okay. So by posing questions, your doubt will be clarified, and also you are making others to clarify. Some may be having a fear of asking questions. So please, hereafter, try to ask questions and then clarify. Okay. Thank you. Thank you so much for your patient hearing. We'll be joining again for the next session at 2 o'clock. So all of you join. Thank you. Thank you, one and all. Okay. Anything else you want to ask? You can ask me. What, Dura? Any problem?
No problem. Feedback
My problem is yesterday your bed was white. Now it has changed after my powder metallurgy. Huh?
Yeah. I have done some editing.
Of powder metallurgy on your bed. Huh? Very good.
Correct.
Yes.
Yesterday was original. Today is duplicate.
Yes. Okay.
Yesterday was nakli. Asli. Today is nakli.
Okay. Right.
After development of the product yesterday. What about feedback forms? Feedbacks.
Don't get tensed. Yesterday we had a very good session on stress management. No. So don't get tense.
Okay.
Huh?
Okay.
Join.
No
Afternoon,
stress.
we'll be posting the link for both all the 3 sessions. You can give your feedback. Okay?
Okay.
Thank you so much.
Okay, thank you very much for nice lecture. Yeah.
Try to assemble at sharp 2 o'clock. We'll have a session.